Okay, let's define a distance function. A distance function is defined this way. You start with a set E, and you define a function that goes from E times E to R. And that means that D is going to take two inputs, two elements of E. Now, to be a distance function, D needs to meet certain criteria. The first one is that for any x and y in E, the distance is positive. You do not have a negative distance. So you have to have a positive distance. First requirement, D needs to be positive. Second requirement is that D of xy equals 0 is equivalent to x equals y. Now, if you think about it, this means that for the distance to be equal to 0, you need both points to be actually at the same place. So it kind of makes sense with the word distance. As you see, that is a second criterion. Third one is that D of x, y, the distance from x to y, is the same as the distance from y to x. So it's symmetric. And finally, the distance from x to y is smaller than the distance from x to z plus the distance from z to y. And if you think about it, here's what it means. The distance from x to y is going to be smaller than the distance if I go from x to z and then from z to y. All right, so if we have all four criteria, what we have is a distance function, and the space E with this distance function is a metric space. If you don't have the second criterion, then what you have is a pseudo-distance function, and ED is a pseudo-metric space. In other words, if 2 points can be at different places, but have a 0 distance in between them, then it's not going to be a distance function, it's going to be a pseudo-distance function. If you don't have the third criteria, which is D of xy equals D of yx, in other words, you don't have a symmetry, you do not have a distance function, you have a quasi-distance function. And you have a quasi-metric space. Let me give you an example, actually 2 examples here, actually an infinity number of examples. Let's choose as a set Rn. So think about R3, that's our space, or R2 is the plane, or R1 is the line. Then you can define the distance dp as the sum of xi minus yi, that are the components of x and y, and you raise this to power p, you add this up, and then you take the pth root of it, or you raise it to power 1 over p. You can also define d infinity, which is the maximum of the xi minus yi, the actual absolute value of this. And what you have is the distance d infinity. And you can verify that these distance functions are actually distance functions. You can verify that dp and d infinity meet all the criteria we talked about earlier. And you can actually do this, and you can look at the PDF document which is on the site, and then you will see how to do this. Especially the last criterion, the one about the inequality, is something to be seen. All right, there is an example that needs to be discussed, and that is D2. And the reason why we need to discuss D2 is because this is the one distance that you're used to. If you look at a bird that goes from one point to another point, then it's just going to use a straight line, and that is D2. And you can verify that indeed the way to compute this distance is in the plane, you take x1 minus y1 square plus x2 minus y2 square, and these are the components of x and y. You add this up and you take the square root. If you know about a few things on Pythagoras, for instance, then you will see that it's actually D2. In other words, this is the distance you will actually see if you use a ruler to measure on the plane. That is D2. It is a distance function, and again, you can verify this by simply checking that all of the criteria that we talked about are met. Another example is in R2, actually with n equals 2 in the plane. This is Manhattan, and you can actually just zoom in a place where Broadway is not nearby. And let's say you want to go from one point to another point in Manhattan. Now, obviously, you cannot go through the buildings, so you're going to have to go through the avenues and the streets. And if you want to compute the distance that it takes to go from one point to the other point, then what you're going to do is actually compute d1. And d1 is the sum of x1 minus y1 and x2 minus 1, 2. And in this case, d1 is a distance function. And indeed, you can compute the time, or actually the distance, probably the time, to get from one point to the next. So let me ask you a question. Start with space E, which is all of the metro stations in Washington, D.C. The distance from X to Y, meaning from one metro station to the other metro station, is the average time to get from X to Y, from one metro station to the next, using the fastest way. Question is D a distance function? Does it meet all of the criteria? Okay, let's verify. Let's check. Is D a distance function? Does it meet the first criterion, which is that it is positive? Well, yes, it does. I mean, the average time to get from one station to the next or to another station is positive. Second criterion. Is it true that the distance of x, y equals 0 is equivalent to x equal y? Well, to get from one metro station to the same metro station, it takes no time. So indeed, if x is equal to y, then dxy equals 0. Now, if dxy is equal to 0, in other words, if it takes no time to get from one metro station to another metro station, unfortunately, it means that the two metro stations are not the same. It's not Star Trek when you can get from one metro station to the next in no time. Therefore, the second criterion is met. Third criterion. Is it true that the distance from x to y is the same as the distance from y to x? And if it takes a few minutes to get from metro station or metro center to L'Enfant Plaza, then it's going to take the same time to go from L'Enfant Plaza to Metro Center. So the third criteria is met. Fourth criteria, which is d of xy smaller than d of xz plus d of zy, which by the way is called the triangular inequality. Well, this one is true as well, because it takes less time to go from x to y directly than to go through another metro station. And indeed, if you go from Metro Center to L'Enfant Plaza directly, it is faster than going to Silver Spring, Maryland, obviously. So all four criteria are met. That means that D is a distance function. Now, if we were in Paris, the situation would be slightly different, actually. We could take all the metro stations in Paris and the average time to get from one metro station to the next, to another one being using the fastest way. D would not be a distance function simply because it is not true that the distance from x to y is the same as the distance from y to x. There are some loops in the network in the metro system in Paris. And for instance, if you come here in the beautiful City of Lights, you will see that the distance from Bodzaritz to Danube on this line is actually different from the distance from Danube to Bodzaritz because you have to go in one direction only. And we're looking forward to meeting you here in Paris whenever you come. Other question. Consider E, the set of all functions from R to R that are defined in 0. Let's define the function D as a function that takes two inputs, f and g, two functions in E, in other words, two functions from R to R defined in 0. And d of fg is defined by the absolute value of g of 0 minus f of 0. The question is d a distance function on E? Okay, the answer is no, it's not. It is a pseudo-distance because the distance between the function that makes x corresponds to x squared to x corresponds to x cubed is going to be 0. But obviously these two functions are different. X squared and x cubed are going to be two different functions, but because they have the same value in 0, d of fg is going to be 0, though the functions are different. So we're in a situation where d is not a distance function. It does not meet this criteria of dfg equals 0 if and only if f equals g. Another example, let's choose a function d that is defined this way. D of xy equals 0 if x is equal to y. D of xy equals 1 if x is different from y. Is d a distance function on E? Okay, let's verify. Let's check all of the criteria. Number 1, is d positive? Obviously it is. Number 2, is dxy equals 0 if and only if x is equal to y? Obviously it is. Number 3, do we have d of xy equals d of yx? Well, if x is equal to y, then y is equal to x. True. If x is different from y, then d of xy is going to be equal to 1, which is the same as dyx. So the third criterion is met. And lastly, if you look at dxy, it's obviously going to be smaller than dxz plus dzy. So the fourth criteria is met as well. D is a distance function, and ED is a metric space. So as you can see, for any space E, you can always define a distance function, at least this one. I'm not saying it's a very interesting distance function, but I'm saying that you can define such a metric space and such a distance function on any set E that you have. Now, I can also define the distance from a point to a set, and it is defined this way. The distance between point A, which is in E, and a part of E, that is x, will be the infimum of all the distance function dAx for A, which is the point, and x, which is any point in x. And what it means is that it is the infimum of all of the possible distance function from A to any point of x. In this case, this is the infimum is the straight line here, and that will give me the distance from a point to a set.